Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on impedance matching. On my previous video, which is the part 16 series discussion, I have discussed the various tapered line. For example, I have discussed the linear, triangular, exponential, and also this Klopfenstein tapered line. This video, I want to focus on an example. How can we actually design the different types of taper line? So this video, I will show you an example. How can we actually design the linear taper line, triangular taper line, exponential taper line, and last but not least, this method, Klopfenstein, is much more difficult. But in this video again, I will have an example. How can we actually design the last, which is the most difficult, which is known as the Klopfenstein taper line. So this will be the part 17 series discussion on impedance matching. So guys, if you're keen to know more about impedance matching, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on impedance matching. This is my email. If you have any question regards on this discussion, please drop me an email. Or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. Let's quickly go through an example. So basically this example tasks us to design the linear tap, triangular tap, and exponential tap, and last but not least, Klopfenstein taper. So the maximum reflection coefficient will be at 0.02. So the idea is to match a 50 ohm load to a 100 ohms so-called characteristics impedance line. So we are tasked to plot the impedance variation and also the resulting reflection coefficient magnitude versus beta L. So let's come to the first one, which is the linear tap. So this is the linear tap. So in short, for linear tap, there's no equation. So how you can actually design the linear tap is you just draw a line from the lower impedance to the higher impedance, and also another line from the lower impedance to the higher impedance. So this will be so-called a tapered line for impedance transforming. So basically you have done this impedance matching through a linear tap line. So in short, there's no formula. So what you need to do is you just draw this to reach to the other side, and on the other side also draw to reach to the other side. So what you can only control will be the L. The longer the impedance matching, the better will be the matching, because we are going to have lesser so-called reflection coefficient. So in short, the longer you can have, you actually have lesser reflection coefficient. But for this linear tap, basically the reflection coefficient magnitude, is much difficult to analyze. So in short, if you want to get the reflection coefficient, you can only do it slow by simulation. So this is the first method. In terms of impedance, basically it will decay in a linear manner, as you can see from here. So in short, you can imagine that the impedance will be 50 and then start to increase maybe 60 here, and then increase 70, and then maybe here 80, and then maybe here 90, and finally they reach here, then they will be at 100 ohm. So basically you can see that the impedance actually so-called increase in a linear manner. So this is the first method that we design for linear tap. Next, let's move on to the triangular tap. So this is the formula to design for the triangular tap. So this will be the impedance variation. So this will be the equation. You can see that in this equation, there are actually two sections. So one section will be from the 0 to half of the impedance matching length. On the other formula is actually from L/2 all the way to the length. So imagine this. The length of the impedance is from 0 all the way to the L. So L/2, which means that half. So let's say if we design this in the ratio Z/L, so half will be at 0.5 as you can see that basically the in full ratio will be all the way from 0 to 1. So if let's say half, we will be at 0.5. So therefore, the equation for 0, 0.2, and 0.4, we will use this equation. As for 0.6, 0.8, and 1, we will use the second equation. So in short, okay, basically, if you need to have more so-called steps to do, let's say you want to do 0.1, 0.2, 0.3, and 0.4, then you will be using the first set of formula. So if you intend to do for 0.6, 0.7, 0.8, 0.9, and 1, then you need to use the second equation. Okay, so let me show you an example, okay, how to design the impedance. Okay, so basically, let's assume this first, okay, so 0.2. Okay, so when this Z over L, the ratio is equal to 0.2, you sub inside here. So you can see that this Z naught, okay, E2, so this I will put just 0.2. So this Z over L, I just put 0.2 as squared. And this long, okay, so keep this in mind. Okay, so this number will be always the bigger number divided by the smaller number, always. Okay, so if the case is reversed, you just need to change the ZL and Z0. So in short, the top one will always be the larger impedance. So from here, what you need to do is basically, if you punch your calculator, okay, this all the number should be add up, should be equals to 0.0555. So you punch your calculator, we show you that this will be at 52.85 ohm. So basically, at 0.2 away, okay, so basically you just imagine at this 0.2, okay, the ratio of Z over L, okay, the impedance value will be equals to 52.85. So basically from here, okay, which means that, okay, let's say this is a taper. So basically at 0.2, let's say it's here. So I know that my impedance, okay, will be equals to 52.85 ohm here. Okay, so this is the first method. So how we actually use the second equation? So as I mentioned that, for example, okay, when Z over L is equal to 0.8, then we need to use the second equation. Okay, so basically the second equation will tell us that Z over L will be equal to 0.8. So you can see this formula here. Okay, so for this Z over L change to 0.8, okay, minus 2. Okay, so basically this will be 0.8 squared. Can see here, so basically I just take the Z and the L and then square it. And then I have this minus 1. Okay, again, this will be always the bigger number divided by the smaller number. Okay, so I don't want to dwell so much on the mathematics. So if you punch your calculator, okay, you should be able to get 94.61 ohm. Okay, so which is 0.8. When the Z over L ratio is equal to 0.8, I will able to obtain 94.61. Okay, so I think if you do this, okay, correctly, okay, I don't foresee you getting so-called issue of getting all this number. So once you have all this number here, okay, so then we are ready to plot the diagram here. So basically these are all the Z value. Okay, so basically this is the ratio Z over L, which I have come up from the table here. So the first one is 0. Okay, so when it's 0, it's about 50. 0.2 is about 52.85 here. So it's around 52.85. And then if you have one more steps, you will be able to plot it, okay, nicer. Okay, so but in short, okay, so basically this is just a illustrate, okay, to show how does the so-called impedance vary, okay, with the length of the impedance matching. So from here, okay, you can easily design so-called the impedance, okay, along the impedance matching, okay, in order to achieve the matching, okay, using this method, which is called the triangular tapered method. Okay, so basically this will be for the impedance. So next we need to calculate the reflection coefficient. Okay, for triangular tapered line, okay, I need to use this formula, okay, for the reflection coefficient. Okay, so this is the reflection coefficient. So this will be beta length. So basically I need to have 0, pi, 2 pi, etc. Okay, so you can see that there are a lot of numbers. So let's just do one. Okay, so when this beta length is equals to pi, which is here. So from here, you can see that basically I just substitute this beta length into pi. So this equation here, as you can see from here, it will be cosine minus pi plus j sine minus pi. So basically this term here will be minus 1. Okay, but if you see this bar here, which means that no negative, so it become 1. So this thing will just disappear in the equation here. Okay, so basically this thing will just disappear. So again, this will be always the bigger number divided by the smaller number. So this beta length here, which is equal to pi, so basically it's pi over 2, as you can see from here. Again, this will be pi, so this will be pi over 2. So let's do a quick, okay, so basically this is half. I told you this is equals to -1 or equals to 1 because of the magnitude here. So I can ignore this one. So this ln 100 over 50 will be equals to 0.6931. So this side pi over 2 is equals to 1. So from here, again, I can easily calculate the reflection coefficient, which is 0.1405, which is written over here. Okay, so what you need to do is basically you sub all the different number into this equation. You should be able to arrive what I actually get. Okay, so basically in short over here, you can see that okay, I actually have also designed the triangular tapered line, okay, by using all this equation here. Okay, so next, okay, let's do the exponential tape. Okay, so earlier on, I have done the triangular. So now let's do the exponential taper line here. So this is the equation to calculate for exponential taper line. So this A is equal to 1 over L, okay, which is the in over ZL over Z naught here. Okay, so over here you can see that I just substitute the A, this thing here. So again, there's a Z over L here. So this is the in ZL over Z naught. Okay, so this term here again, I have done the calculation earlier on, which is equals to 0.6932. So I just sub it here. So this case here, I just do the ratio of Z over L as 0.2. Okay, so therefore I substitute them as 0.2. And if you punch your calculator, you should be able to arrive at this answer, which is 57.43 ohm. Okay, so basically this will be the Z over L equals to 0.2. Again, if you sub all this number, okay, you should be able to find the impedance. How does the impedance change with the length of the impedance transformer or impedance matching? So basically with this, you actually again can also draw the chart. Okay, I will draw the chart lastly so that to do a quick comparison between the triangular, exponential, and Klopfenstein tapered line. Okay, so this will be the reflection coefficient for the exponential tapered line. So this is the equation here. Okay, again, I'll show you one. So basically, I pick up the easiest one. So when this beta line is equals to pi, so when psi pi is equals to 0, so all this thing will be equal to 0, which is here. Okay, so again, if you put all this number inside, okay, you should be able to get this. So once you get this, okay, you actually can draw the graph. Okay, like I mentioned earlier on, okay, the graph I will show you on the last page. So basically, from here, you can see that I have successfully designed, firstly, the linear tap line, followed by the triangular tap line, and this, okay, I actually have also finished discussed how to design the exponential tap line. Okay, so before I continue, guys, please help this channel. Okay, please help to like this video. Just spend a few seconds to like this video. Okay, so this can help this video to reach out to a larger audience. So guys, help me press the like button now. If you have learned something from this video, okay, please consider to subscribe and turn on your notification bell. Okay, so let's continue on the last method, okay, which is the Klopfenstein method. Okay, so this is the most difficult way to design. Okay, you can see that there's a lot of equation. Okay, but don't worry, I will make it easy for you to understand how can we actually design the impedance matching using this Klopfenstein tapered line. Okay, so this is the equation to design the Klopfenstein tapered line. Okay, so let's go through this. So basically, this reflection coefficient not here, okay, will be by this equation. Okay, so you can easily so-called estimate as this equation here. Okay, so basically will be half. Okay, so the in over ZL over Z naught here. So this is the equation here. So I can easily calculate, okay, this reflection coefficient not is equals to 0.3466 here. Okay, so next, okay, I can calculate the A term, okay, which is by this equation here. So from here again, I can calculate my A term, okay, which is equals to 3.543 in degree. Okay, so once I got this, you can see that from this equation, okay, I will have this term here. I have the A term, so therefore I'm capable to find this term also. I'm also able to find the A squared term. I come to how to find this later on. Okay, so basically this is the in general equation. Okay, so again, okay, so I need to let my ZL is equals to 0.5. Okay, so once I know my ZL is equal to 0.5, this term here, okay, which is half, okay, in, which is 50 multiplied by 100, I calculate, which is equal to 4.2586. So basically, I found this term here. Okay, next will be on this here. Okay, before I found into this, okay, so basically, I let the ZL equals to 0.5. Okay, so this thing is equal to 0.5. So from here, you can calculate that 2 over half, this will be equal to 1. So 1 minus 1, it will be 0 to A. So once you come to 0 to A, you can see that this table here, this means that this whole thing will become 0, which means that all these things will be equal to 0. Can you imagine this? So all this will be equal to 0. So therefore, okay, my in Z will be equals to just this term. So therefore, from here, okay, I actually have calculate, okay, so which is 4.2586. Okay, remember, I need to get the impedance, which is the ZZ here. So therefore, I do a reverse here. So from here, I calculate that my ZZ term will be equal to 70.71 ohm. Okay, so I will show you the chart, okay, on the last page. But over here, you can see that how actually done the Klopfenstein tapered line is basically is a little bit tedious. Okay, so you need to have a lookup table and then basically substitute all the number inside. And after that, you need to do a reverse in order to get the impedance. Then after that, you will be able to achieve the impedance value. So basically, when Z over L, okay, having a ratio of 0.5, the impedance is actually at 70.71 ohm. Okay, again, I will highlight this on the last page here. So I have done in terms of the impedance. Okay, so let's quickly done in terms of the reflection coefficient. Okay, so the reflection coefficient will be by this equation here. Okay, again, you can quickly do some calculation. So this is the uh, reflection coefficient and the knot here. Okay, basically will be governed by this equation, which I have explained early on. So again, if you punch your calculator, you should get this 0.3466 here. So this is another equation that you need to calculate. So basically, when you punch your calculator, this is in terms of degree. Okay, so I just leave it back in the degree form. Okay, so now we are ready to do this equation here. So for example, okay, let's say we let this beta L is equals to 2 pi. So you can see from here, this will be equals to 2 pi. And I need to convert them into degree. Pi is equals to 180 degree. So therefore, from here, I can calculate that this term here, when they actually combine, they will be the number equals to 129,587. Okay, which means that 2 multiplied by 180, then I squared it, then I minus this term in squared. So I will be able to find this number as 129,587. Okay, so this I also punch my calculator. Okay, keep this in mind. All this must be in degree because all these are all in degree. So therefore, I actually get the answer of 17.3 in degree. Again, all these you can actually punch your calculator. And finally, you get the answer of the reflection coefficient, okay, which is at 2 pi, which is 0.02. Okay, so with this, you actually can also calculate for all the points here. But let me do a quick conclusion. How does the thing actually look like? Okay, so earlier on, I have done the linear. Okay, so linear is very straightforward. You just need to have the 1 to 100. You just draw one straight line all the way down, all the way to this point here. Okay, so this is actually for the linear. Okay, so the next one that I actually do is actually the triangular way. So this is the triangular, okay, which is the dashed line. Okay, after that, I actually do in terms of the exponential. So this is the exponential with the dotted line. Okay, so this is actually the exponential. And the last one that I draw is slightly more challenging to design. Okay, so therefore this is a Klopfenstein method here. So over here you can see that I actually plot the 3 method, or maybe you can imagine that the 4 method which include the linear. So basically in short, this diagram here actually shows the 4 types of taper line: the linear, the triangular, the exponential, and the Klopfenstein impedance tapered line. Okay, let's come to the reflection coefficient. Okay, so this is the reflection coefficient, okay, for all the 3 types here. Okay, firstly will be the triangular, okay, the Klopfenstein, and also the exponential. Okay, so I just want to point out something, okay, which is the last method, which is the Klopfenstein method. Okay, so if you still remember, this is the equation, okay, to compute the reflection coefficient for the Klopfenstein method. Okay, but if you take a look over here, okay, so basically you can see that this thing minus A, so this beta L must be greater than A. If it's smaller than A, this will be minus number and this will not be usable. So from here, I can calculate that this beta length is actually equals to 1.13 pi. Okay, which means that after this 1.13, this will be a pass band, okay, for this Klopfenstein tapered line. Okay, if those all here is not pass band, but after this 1.13, this will be the pass band. Okay, so what does this mean? Okay, the Klopfenstein tapered line can give the desired response, okay, the reflection coefficient, okay, to be maximum at 0.02. So over here, you can see that I don't actually can guarantee that the reflection coefficient will be at 0.02. But after this line onward, okay, I can actually guarantee that the reflection coefficient, okay, will be maximum at 0.02, if not lesser than 0.02. So basically, in short, over here, I have so-called designed the Klopfenstein, okay, tapered line. Okay, so as long as the length is more than 1.13, I actually meet the criteria to have less than 0.02 reflection coefficient. So basically, this is what it means. Okay, so and also want to highlight this, the method to design this Klopfenstein tapered line, they are actually much smaller, or which means that the length of the impedance matching is much more so-called shorter as compared to the other method, okay, which is the triangular and also the exponential, as it mentioned over here. Okay, so you also note that, okay, like the step Chebyshev matching transformer, okay, the response of the Klopfenstein type has equal ripple. Okay, you can see that, okay, for this Klopfenstein method here, okay, which is the solid line, okay, you can see that they have equal ripple. And you can see that the maximum of the ripple will be 0.02, which I have calculated early on. So basically with this, I like to end my discussion. Okay, so over here you can see that I have successfully designed 4 types of taper line. Okay, the first one will be the linear. Okay, so which is the much straightforward. Okay, so if you remember, you just need to draw the line from the lower impedance to the higher impedance. That's it. The second method, which I have discussed, which is the triangular taper line. Okay, so, and then after that, followed by exponential. And then last but not least, okay, I actually have discussed how can we actually design the Klopfenstein taper line. Okay, so this method is the most challenging. Okay, but this method actually benefit because you can see from here, the length of 0.02, okay, basically they are much shorter. So what does this mean? For example, let's say, okay, I'm using the triangular. So to ensure 0.02, you can see from here, okay, so this thing bounce up may be higher than 0.02 over here. Okay, so over here, then I will be able to achieve 0.02. So therefore, you can see that, okay, this method, okay, actually has a longer length, okay, because over here, you can imagine they are actually higher than 0.02 over here. So let's say 0.02 is over here, let's say, then I actually can guarantee over here onward for the triangular. So as for the exponential, it's the same thing here. You can see that this method cannot pass, still cannot pass the 0.02. This method also cannot. This method, let's say it passed already. So therefore, you can see that the length must be from here onward, then they will be called the pass band of the exponential taper line. So basically, in short, okay, you can see why we want to design the impedance transformer using this Klopfenstein, okay, because it has the shortest length, okay, in order to achieve, okay, the desired reflection coefficient. Okay, so with this, I like to end my discussion. Okay, please help to like and subscribe. Once again, thank you so much for strong support. I hope to see you guys soon. Bye for now. Thank you.